In this problem, I'm going to give an example of proving an identity using the binomial coefficients. And this has new notation in it, but the binomial coefficients I'll abbreviate that. They are simply the number of combinations that we've been talking about in the lecture, C, N, K. This is the number of K element subsets that can be chosen from an N element set. And you might use the mnemonic that C stands for committee. This is the number of K member committees that can be chosen from an N member club. All right. And CNK is sometimes written as C as a function of NK, and it is also often written as just NK above each other in parentheses with no slash in between. It is not a fraction. It's just N above K, and this is the notation that's being used in this problem to notate the binomial coefficients. Okay, and it says use the definitions of factorial and binomial coefficients to show this is true. And first, let me just give a little bit of background and remind you of Pascal's triangle. And this is C0, 0, C0, 1, C1, 1, etc. These are the binomial coefficients, and we found that they had values which, in any particular row, when you summed them, was equal to 2 raised to the power of n. And the first row is n equals 0. 2 to the 1 is 2. You sum the 1 and the 1 to get 2. The 1 plus 2 plus 1 gives you 2 squared, or 4. And 1 plus 3 plus 3 plus 1 is 2 to the third, or 8. Okay, so you sum them in the rows. And so in other words, what happens is that in row n of Pascal's triangle, the total number, the sum of the numbers in the row is equal to the number of subsets of an n element set. So for example, n equals 2 in the n equals 2 row here, and we have 4 different subsets, possible subsets of a 2 element set. And the first element, C2, 0, is the number of 0 element subsets of a 2 element set. The second one, C2, 1, is the number of 1 element subsets of a 2 element set. And finally, C2, 2 is the number of 2 element subsets of a 2 element set. And so these binomial coefficients add up to the total number of subsets of a set, that is the size of the power set, and each binomial coefficient gives the size of the power set of sets of a certain size. Remember, P of S is the set of all subsets. It's the power set of S, and Pk of S is the set of all K subsets, K element subsets of S. Okay, so these are actually can be interpreted as the pk values. So that CNK can be interpreted as the size of P of S with a subscript K, where the size of S is n. Okay, so that's just a bit of review. Let's go back to the thing we're supposed to prove here. The sum of these two is equal to that one. And these are represented here as 3 different binomial coefficients. The sum of these two is equal to that one. And that's how we actually create Pascal's triangle. We just add up the 2 numbers above it to get the one below it. And if there's only a 1 above it, it's a 1. So all the way down the edges of the triangle, we just have 1s. And so, for example, the next row of the triangle is 1, 4, 6, 4, 1, because we've added the 1 and the 3 to get the 4, the 3 and the 3 to get the 6, 3 and the 1 to get to 4, etc. Okay, so this is actually, I'm asking you to prove the rule that we use to construct Pascal's triangle, and it's right here. And if you label these things C3, 1, for example, you'll see that these are the numbers in Pascal's triangle. Yeah, the n goes above the k in this notation here. Okay, so for example, if we have CNK is C3, 1, then n is 3 and k is 1. And you'll notice that if we go from k to k, if we leave k in the bottom and then subtract 1 from n, we go from 3, 1 to 2, 1. We leave the 1 the same, subtract 1. So that really is n minus 1 k here. And if you go up to the left, you'll see that they both go down by 1. The 3 goes down to a 2 and the 1 goes down to a 0. So this really does represent the 3 elements in one of these little triangles. And this one really is supposed to be the sum of the other 2. Okay? So now I'm finally going to do the problem where I use the definition of the CNKs to prove this relationship. So I'm going to hope I have enough room down here because there's a little bit of algebra involved. I'm going to go n minus 1 over k minus 1 plus n minus 1 over k. And I'm going to write that as Cn minus 1 comma k minus 1 plus C n minus 1 comma k. And now I'm going to plug in for the values of the c's. And we have the n minus 1 factorial in the numerator. Now I have n minus 1 minus k minus 1. And if I distribute that minus sign, I get minus k plus 1. And that thing is factorial. And I also have k minus 1 factorial. Okay. I'm also going to write the next term, and it has an n minus 1 factorial in the numerator also. And it has an n minus 1 minus k factorial in the denominator, and it has a k factorial in the denominator. Okay, so I've just used the formula for the C and k, except here we have some n minus 1s and k minus 1s, and so I have to figure that out. Now what I'm going to do is I'm going to go ahead and make a common denominator out of both of these terms. Okay. First of all, I notice that the minus 1 and the plus 1 here cancel out. This and this cancel out. And this is n minus k essentially in the denominator here, n minus k factorial. Let's see here. N minus 1 minus k. Let me get the algebra right on this. I'm going to continue this. I'm looking over at my solution here. Maybe I shouldn't look at my solution. Yeah, I have to do this. I'm going to make a common denominator. And I'm going to write this next step. N minus 1 factorial all over n minus k factorial after I've canceled those ones, and then k minus 1 factorial plus n minus 1 factorial all over n minus k minus 1 factorial. I just rearrange those terms here, and then k factorial. Now to get a common denominator, I'm going to multiply the one on the left by k factorial, by k. I see what I'm going to do here. I'm going to take k minus 1 factorial, and I'm going to multiply it by k to get k factorial. Okay? And when I do that, that will give me, this thing becomes k factorial. And in order to compensate for the k in the denominator, I'm going to multiply by k in the numerator. I'm also going to, and so I've gotten that part of it the same on both sides. Now I'm going to multiply top and bottom by n minus k minus 1 in the first term. Okay. And then, in order to get the n minus k factorial in the denominator of the second one, I'm going to multiply by n minus k factorial, top and bottom. Okay? And now I've got a common denominator with these things. And I'm looking over at my other work here, and I'm trying to figure out what I did differently here. N minus 1 minus k minus 1, n minus 1 minus k. And so let's just go ahead and follow this through. I won't look at my previous. N minus 1 factorial times k times n minus k minus 1 factorial all over n minus k factorial, and n minus k minus 1 factorial. Okay, this is now the common denominator, and now I'm going to add to that the numerator over here, which is n minus 1 factorial, n minus k factorial. And let's see here. I can factor out an n minus 1 factorial. I'm afraid I'm messing this up and taking too long. And I'm going to stop here and restart this video where I left off.